So my name is Maria João Valente. I'm from the Technical University of Denmark, from the National Food Institute, and I'm a postdoc working now at the Panoramix. Within Panoramix, we collected samples from the environment, from food samples and from human samples, including blood and human breast milk. And then we're trying to figure out what are the chemicals that are present on those samples, what are the risks entailed by those chemicals on those samples. And for that, we're using an approach that includes this high-throughput effect-directed analysis, or EDA. Using EDA, we can actually try and find out what are the chemicals within these samples that drive the potential adverse health outcomes. So in our group, we're mainly dealing with the reproductive toxicity. One of the main targets of chemical contaminants is androgen receptor, which is involved in development of sexual characteristics during the development of the fetus. So our bioassay included in this Panoramix project is anti-androgen activity. And this is basically the approach that we're using. So here I only have 3 types of samples within all of those that I mentioned. So we have our main focus is the European exposure. So here we have blood collected from European adult donors and also only Danish donors. And then we also have some cord blood also collected at a Danish hospital. What we did was basically we do a chemical extraction. We then have the whole mixture of this complex mixture of chemicals that we test on different bioassays. In our case, we're testing in the well-established bioassay for androgen receptor activity. And then this extracts also follow analysis. For this purpose, a non-targeted analysis, because we kind of need to know what's actually in there. And using also HPLC method, we can also fractionate the samples. And then we go around and test those fractions. And the idea here is to say, okay, if we have an active sample, what chemicals are triggering this effect? So by testing the fractions of these samples, we can point out which fractions are active, and then to chemical analysis, we can match and say, these are the chemicals present in this active fraction. So this is what we did. And then here I can tell you that there's some differences between the only Danish adult blood and European adult blood. We can see antagonistic effects for the whole mixture in the European blood. We cannot actually see anything on the Danish adult blood. We don't have an explanation for this, but it could be also due to the distribution of males and females in these samples, because it's unknown to us. But then we actually see a lot of effects on the Danish cord blood. Although we didn't have any effect here or significant effect on the Danish adult blood, these 3 samples were fractionated, and then we tested all the fractions. Each point here is a fraction that was tested in this bioassay, and then the darker ones are the active fractions that we identified in this bioassay. And then there was a matching of these fractions with chromatograms obtained from the non-targeted analysis. And now we have some candidates for these effects. This work is not concluded yet because we still need to confirm these chemical compounds, but I can say that we find some pharmaceuticals, especially in the blood, which makes sense because it's the most potent sample. Some things make sense, like for instance, we have this pharmaceutical that is the analgesic used for the delivery of the baby, so it makes sense that it's in the cord blood. We have some natural products and some endogenous compounds. So this is what we have so far in this part, but then what we need to further understand is whether these single chemicals that we could identify here are actually active in our bioassay. So we'll do an approach backwards. So if we know the chemicals, we'll test it individually and figure out if these are actually the risk drivers of AR antagonism in these human samples.